here. So that's what we start with at the very top, where it talks about how in order to add or subtract radicals, you need to have like radicals. And it's just like x's and y's. If I ask you if x and x squared are like terms, you would say no. While they're both x's, they also have to have the same power. Clearly, like x plus a y, we can't add those together because they're not like terms. We can only add like terms. That's something you've known for a very, very long time. It's pretty much the exact same thing when we're dealing with radicals. So when I simply ask you in these first three to tell me if these radicals are like, two things have to be true. The number underneath, the term underneath, it's called the radicand, but the number underneath has to be the same. So we're good there. But it also needs to be the same type of a radical. So notice how these are both square roots. So it's implied that there's little 2 index numbers here. Those are the ones that you're most familiar with. As long as they have the same little index number, the same number underneath, these are like radicals. Okay. If we go to that second one, so this in terms of what I'm just asking here, you would say yes, those are like terms or like radicals. Second one is similar with one big difference. So these both have the same number underneath. So initially we start thinking, yeah, maybe those are like radicals. But what you're going to notice with these now, notice how this one is a cubed root because the little index number there is a 3. The fact that this doesn't have one written in is implied that this is a square root. Those are not like radicals, okay? So in this case, you would say no. So the same number underneath, and we got to have the same index number. And then this one, pretty clearly, while these are both square roots, this is the square root of 3 and a square root of 2. Clearly, those are not the same number underneath, so we would say no to that one as well. So same number underneath, same index number. If they are, in fact, like terms, you're going to do the same thing you do with x's and y's. You're just adding or subtracting their coefficients. So what I mean by that, so go to number 1. What you would want to identify in number 1, you have the square root of 11 here. We have another square root of 11 there. You're basically just combining like terms. So you're going to add those numbers that are in front. Oh, see him.
I wasn't installed in.
Oh, I'm sure.
I figured I would.
Okay. So if we're going to add these like terms, what we have is a positive 5 and a negative 8. If I'm just going to lump those together, that ends up giving us a negative 3. And then just like with x's and y's, we don't actually do anything with the variables. We just leave the radical alone. So it's just a negative 3 root 11. If you look at the other terms, we have a square root of 3 here. We have a square root of 3 there. Those are like terms. So we're just going to add their coefficients. So a positive 6 and a negative 19 is a negative 13. And then we leave the square root of 3 alone. All right. So number 2, we can quickly identify, I would think, these are both square roots of 2. Square roots of 2. So we're going to add them up. Just like if I gave you like a 2x plus an x, there's always implied to be a 1 in front of the x. It's the same with the radical. There's a 1 in front of this radical. So when we add those, you're just going to have 9 square roots of 2. Yeah, Nora. What's it? Okay. Let's go here. Let's see. I need one too. Now think about it. Okay, so with that, do 3 and 4. Because the 3 and 4, 1, 2, 3, and 4 should be about as easy as anything we've done almost all year. So those are like terms. We're just adding them up. All right, see what we get. Miss somebody else? Yeah. All right, Joel, are these like terms?
Yes.
Yep. So what do we end up with when we combine those?
Negative 9 and 5.
Good. Negative 9 square root of 5. There is a 1 right here. 1 minus the 10 is a negative 9, and then we leave the square root of 5 alone. Okay. All right, 4. Here's the reason I give you this now. When we do this, how many root 6s do we end up with here? What is root 6? What do you think, Armando? Good. It's just a 0 here. Okay. Don't. So, and the reason I give you this is don't put like this is a root 6 and then think that nothing in front of it means there aren't any. If you leave this, you're saying that there is, in fact, a 1 in front of this. So 0 is your answer. I would take 0 root 6. That's not wrong. Okay. That's very much correct. But anything times 0 is ultimately a 0. So 0 would be kind of that simplified final answer. All right. So now let's go to number 5. And let's say now I told you to add those together. What we would hopefully recognize, these are clearly not like terms, or not like variables. So this is a root 8, and this is a root 18. So right now we would not be able to add them. The homework you turned in yesterday, the one that I just gave back to you. What we did though yesterday is these are probably ones that can simplify. Since these are a little bit bigger, these are ones we could probably break down. So that's what we now want to do. So I am going to look at 8. Think about what your perfect squares are. Again, our perfect squares are 1, 4, 9, 16, 25, those list of numbers that we had that very first day of all of this. For 8, do we all agree that 4 is a perfect square that would go evenly into 8? Yeah, so we're going to use 4, and then 4 times 2 would give us the 8. Then we're going to do a plus, and we need to do the same thing for the 18. So we want to come up with a nice perfect square. So from our list over here, that's a perfect square that goes into that. Caden, that's what? Good. So the 9 is our perfect square, and then 9 times 2 gives us that 18. So initially, we're going to do the same thing we did for the homework. We're now going to go ahead and take this 5. The square root of 4 is ultimately a regular old 2. So we're going to rewrite that as a 2. And then the root 2 you can't do anything with. If we do the second part, the square root of 9 is a 3. And then that's going to be a root 2. We can simplify this a little bit further. This 5 times 2 is a 10 root 2. Once those are completely simplified, now if we think back to what we did in those first 4, don't these actually then end up being like terms? They're both square roots of 2. So we can now go ahead and add them once we have simplified them. These are both root 2s. We have 10 here. We have 3 there. So we have a total of 13 root 2s. So if they don't look similar or the same immediately, if they simplify, there's a reasonable chance that maybe they are. Okay. All right, so same thing with number 2. Right now, these are not like terms, right? This is a root 12. This is a root 48. So we can't do anything with them. But those are both pretty big numbers. Pretty reasonable chance that we could find some perfect squares that's going to work for these two. So do that real quick. Find perfect squares for 12. Find perfect squares for 48. Get that part down. This is, again, what we just got back for the homework. All right, so try 12 and 48. All right, see if we can get those broken down. Here's our list of perfect squares here. I hear a lot of us pulling out the paper. That's good. Okay, if you have those in front of you, those are your candidates that you're just testing. All right, Jada Robin, I'm going to give you the nice one. What did you use for 12, Jada? And what then? Good. So our perfect square is 4. That's what will go nicely into 12. That's a perfect square. And then we're left with the 3. Can't do anything with the 3. All right, 48. Anybody think got that guy? Omar? All right. Omar says 4 and 12. So is 4 a nice perfect square? Does it go into 12 or 48 12 times? Yeah. All right. Did we all pick 4 and 12? All right, Maddie. All right. So now here's nobody's wrong with this, but we could go bigger. So let me create some space over here. So Omar is correct. Maddie is also correct because 16 is going to work as well. So here's how I'm going to do this. I'll do this over here. I'm just going to recopy this. What was it, Maddie? 16 and what? Good. Here's why we said yesterday, if at all possible, kind of work your way up just to make sure we get the biggest number because that's the easiest. But if Omar does this, we should still be able to get through this. All right, so let's kind of do the way we have it right now. I'm guessing a lot of you had 4 and 12. Okay, I'm sure he's not the only one. So you're not wrong. Let's see in the future if we get to it. We will have a little quiz on all of this on Friday. So let's say you did this. We want to be able to now kind of understand we need to do a little bit more. So we take this 8. The square root of 4 is a 2 and then a root 3. So what that first one simplifies to be is a 16 and then a root 3. All right. Minus. Then I'm going to drop this 5. The square root of 4 is again a 2, just like it was in the previous part. And then I'm going to leave that root 12 alone because that's not a perfect square. So if we go about it that route, you're going to get 10 root 12. So where you need to now be careful, you got to understand 12 is a reasonably big number, and it's also probably a number, we just did it, I suppose, right? Weren't we able to break down 12 earlier in this exact same problem? So if that you encounter that, that means we need to do a little bit more work with this. We need to make sure that we're simplifying that all the way. So what we would now need to do with the 12 is just like we did up here. Didn't we take 12 and do a 4 times a 3? So we would have to do that again for this 12. Still get to 16. This guy's pretty much done right now. Can't do anything with it. But then this becomes a 10 times a 2 and then a root 3. So once again, I'm just going to recopy 16 root 3. This now becomes 20 root 3. Notice how they now actually do end up becoming like terms. They're both root 3s. So we can simplify that to be a negative 4 root 3. That is our final answer. That's correct. But again, look at how many steps that took us if we do it that way. A lot going on there. Okay. So ideally, if we can get the biggest number, it's going to make your work a little bit bigger. So Maddie gave us 16 and 3. Watch how this one now play out. So let me get rid of these so I have a little room to operate. This would be 8 times 2 root 3. That's our 16 root 3 that we kept getting over here. This would now become 5 times what? What's the square root of 16? Matt, Julia? 4. And then our root 3. Well, 5 times 4 then gives us that 20 root 3. Don't we get the exact same thing? 16 minus a 20 is a negative 4, and then you're going to get that root 3. It's probably only a matter of time before you pick one that you could have gone bigger on, and you want to be able to continue on further. So both of them are correct. You just got to recognize when can I continue to go further. Either way, though, this should give us a negative 4 root 3. Okay? All right. Next one. Number 3. Same. Find ways to break down 24 and then find ways to break down 54 with our perfect squares. And hopefully the list is great. Hopefully we start doing these enough. We start kind of knowing it's 4, 9, 25, those nice perfect squares. So see what we come up with for these. All right. Jacob, 24. What numbers did you use?
4 and 6.
Good. 4 times 6 gives us 24. 4 is the perfect square. There aren't any bigger ones. All right. Then we go to 54. Joe M. What'd you get?
9 and 6.
Good. 9 times 6. The 9 is our perfect square. 6 we can't do anything with. It's also nice because don't we end up with both root 6s? So we're going to be able to combine them at the end once they both get simplified. So this would become 3. The square root of 4 is a 2. The square root of 9 is a 3. So 3 times 2 then in that first one is 6 root 6 minus a 3 root 6. Like we said at the beginning, these end up being the same. So we can now go ahead and add those. A positive 6 minus a 3 is a positive 3. And then leave that root 6 alone. All right. All right. 4 and 5. Try both of those. We're going to kind of circulate and see where we're at. It's not much different than yesterday, what you did. You're just doing 2 of them in 1. And then if they end up being the same, we're going to add them. So try to knock out 4 and 5. And then we'll do a cubed root on the next page. So last 2 square roots. If you have a question, do you have factor sheets or did you put them in here?
There should be in there. I can make more copies. I might still have a couple in my bag if you need one. If you want, you don't need to though. It's up to you. If you like anything, that's fine. Right.
No, you're sure fees though. So for 80 would be good. If you can do it at 80, start searching. So like here's a perfect square. Then get a bigger perfect square right here. But we start dealing with the 125. We don't go that big. So say
You know, it's 6 minutes.
635. But yeah, as long as it's under 100.
Right here. That's right, 6. That's what we just read. That's 3.
Okay, 2 things. I put this first. Not that you have to put it first, but you're also going to do 9 times the square root of 4, which would be 2. So put a perfect square first. So do that first. And then the second thing is that root 20 is kind of a big number. So do you think we're going to be able to break down 20 further? With what? You could, but what's a perfect square that doesn't do 20? So what that then means is there's a bigger number in our list. To make your life easier, once we identify there's a bigger number, I would erase these 2 and start working my way down the lists until I find a bigger number that goes with it. But you're just going to do it here though. Don't necessarily do this. What you just write. It's kind of like if I give you 2x plus 6y plus 5x plus 2y, you go ahead and add these. And we go ahead and add these, but it is still these guys. It's still you add from each other. So that's a square root. Second, is there another perfect square that involves 20? squares, you're going to break this down further. So that's the one thing you're going to do multiple steps of it. What that becomes is you have a bigger number on your list. So to make it easier, I would kind of go through the perfect square list and find a bigger one. So that's a more squares. Four would work. But they're bigger ones, so I'm trying to work towards 16, 16, 25. Because you're going to get a little bigger, it's going to be a little bigger. Where's your sheet about the perfect square? Get an 8 or 10 a perfect square. So while 8 times 10 would be 8, this isn't the same way that I have a perfect square. So the only thing we really want to investigate are the numbers of elements 4, 9, 16, 25, 36. Those are all perfect squares. We just don't write this. We just leave that. It's kind of like your 2x plus 4y. We just leave it. We can't look at the other, but that is still there. I would just start about halfway through 125 to try 60. Do 125 rather than 60. Once you take those are great. It was way 36. All right. We're getting there slowly. All right. So number 4. Caden, what did we just say for 125? You just got it. Good. 25 times 5 would give us the 125. Walking around, most people were getting that one. This one, now be careful, because I probably saw maybe 5 or 6 people throw down a 4 and a 20. And while that's not wrong, so that's certainly right, there's nothing wrong with that, won't 20 break down further? And because of that, to make your life as easy as possible, what that really means, instead of stopping at 4, that means there's probably a bigger number on your list. Doesn't mean there's probably a bigger number. That means there is a bigger number on your list that's going to work. All right. So if that second number is something you're going to be able to break down further, I wouldn't go down that rabbit hole. I would try to find the bigger number first. It's going to make your life easier. So as we went down the list, 4 worked, but it's just not the smallest. Does 9 go into 80 evenly? No, so that's not even a consideration. Did 16 go into 80? Yeah, that's our guy. It went in there how many times? 5 times. So 16 is our biggest number. And then nicely, notice how the radicals are going to end up being the same. These root 5s are going to be the ones we can't simplify. They're going to end up being the same. All right. So what this then becomes is 4 times 5. The square root of 25 is a 5. This becomes 9 times a 4 with the square root of 5. So what we really have is a 20 root 5 minus a 36 root 5. And then I saw a number of people have this, so that's good. Negative 14 root 5 should have been that answer. All right. Yeah. Marla? What's that? Or negative 16. Yeah. Sorry. Good call. All right, negative 16 root 5. Okay. Number 5. When we go to separate this one, 12 we've already done today. We said that's a 4 and a 3. These numbers should have been a little easier to come up with. And then 8 is a 4 and a 2. So not a lot of options for a 12 and an 8. So the first one, this is 7. Square root of 4 is a 2. Same here. The square root of 4 is a 2. We can now multiply those two numbers in front. So the 7 and the 2 make 14 root 3s. The 8 and the 2 multiplied together make 16 and then root 2s. And then it's easy to kind of get programmed because we just did 4 in a row. where when we simplified them, our radicals nicely end up being the same thing because that's sort of the section that we're on right now. So it's intended for them to be the same in a lot of these, but they're not always going to end up being the same. So we see this is a root 3, that's a root 2. We can't combine those. You just leave that as your final answer. Okay, you don't need to write anything. You just leave that. That's your final answer. It's basically the same as if I give you 2x plus 4y plus 6x plus 10y, we add the x's together to get 10x, and then we add the y's together, 8x, and then we add the y's together, that, to get 14y, but then we just leave it. We don't have to write anything along with that. That's just your simplified answer. It's the same here. Just leave this that way. Okay? All right, next page. It's just basically a little, we basically just want to be able to do these problems. So if I look at this problem right here, it says decide whether this is a true statement or if it's a false statement. If it's wrong, there's something we can do with it, then we want to correct it. All right. So if I look at this one, this is the first cubed root that we have done. So first, this is a cubed root of 8. This is a cubed root of 8. Are those like terms? Yeah, same index number, same number underneath it. So we can definitely combine those. 5 minus a 4 is a 1. Cubed root of 8. So in terms of is this correct? Largely, it's not wrong necessarily. But when we eventually, again, take a quiz, test, whatever, especially if it's multiple choice, what is the cubed root of 8 equivalent to? If I simplify this as much as possible, what do you cube to get an 8? Okay, 2. So that just is a good old-fashioned 2. All right. All right. Is there another? Is that the only cube root I gave you? Yeah, let's do one more of those so we can talk about the bottom. So if I did the next one, is this guy fully simplified? Meaning, can we simplify a root 2 any further? Does it break down at all? No. Does the square root of 5 simplify any further? No. Are they like terms that we can add together? No. So that's it. There's nothing we can do with this. So your answer here would be just yes, that is a fully simplified answer. It's like the last one on the last page. There's nothing we can do with that. They're not like terms. We can't simplify it any further. So that one is a yes. The one above, we could do a little bit more work. We can simplify that to a 2, but this one is fully simplified. All right. 3, this right away is a no because we're going to be able to simplify both of these. So hopefully we would recognize that pretty quickly, that the 18 can be broken down. We'll use 9 and a 2. The 50 can be broken down 25 and 2. So certainly that's one that we can still do some simplifying with. All right, this becomes 7 times 3. The second one is 2 times 5, and then our root 2. First expression is a 21 root 2. The second one is a 10 root 2. They both now do end up being like terms, so we can add those together and get 31 root 2s, not a 3. All right. So kind of the same stuff, but that should be what we do for number 3. All right, we're going to skip 4 because I want to, in the last 5 minutes here, do 1 or 2 on the bottom so you understand how to do these. So go to the last problem, last 2. Instead of multiplying, we want to multiply these together. So I have this quantity here is going to get multiplied by this quantity here. It is, again, very, very similar to if I gave you 2x times 6y, you would multiply the two numbers first. So it's the same here. Take the numbers in front. So the 5 and the 2, those get multiplied together. So those are going to be 10. And then since this is a root 3 times a root 7, it's our little property for multiplying radicals. As long as it stays underneath the radical, we can do 3 times a 7, and then that is a 21. If that can be simplified, we need to simplify it. So if there is a way to break down 21, we would need to do that. So let's go through our options here. One we never really worry about. Does 4 go evenly into a 21? No. Does 9 go into 21? Nope. Does 16 go into a 21? Once we get to 25, it doesn't make any sense. It's actually bigger than the number that we have. So there's nothing we can do with that one. That's your answer. You just multiply them together. All right. 2, however, when we multiply them, you're going to take the 4 and the 5. That would make 20. And then underneath the radical, you're doing 6 times 2, which gives us a 12. We've done 12 like 5 times today already. So of all the ones, we should know that 12 can definitely be broken down further. All right. And that is by using a 4 and a 3. So if we multiply and we end up with something that can be simplified, then we need to go ahead and do that. So this is 20 times a 2. The root 3 we can't do anything with. So that is 40 root 3. Okay, last one. 2 times 3 will give you 6. And then underneath the radical, the 8 times a 5 will give you a 40. I don't think we've done 40 yet. But what's the perfect square that goes into 40? The obvious one here. 4. So 4 times 10 will give you the 40. This is a 6 times 2. So we get 12 root 10. All right, and then that would be our answer. Okay? Oh, she left without giving homework. All right, today we do have homework, though. We don't get off today again. And then just a heads up as well, we have a quiz on Friday. So tomorrow we'll kind of review all this together. All right, it's front and the back. Okay, so front and back. Okay, I'm gonna do that again. I gotta start sleeping on this. That's how I usually differentiate those. All right, let me save this.